I'll be talking about a joint work with Alexander Petrov. And the subject is understanding the homology of say smooth projective geometrical integral variety over field K, which is not assumed to be separately closed. So yes, here's a separable closure, and gamma will be the absolute Galois group. And in this situation, so we have derived category of our shapes, and then we can consider this total complex. So this is an object derived category, which is a which corresponds to a complex of shapes of ZL modules. So that's analytic integers with the action of the Galois group. So this is and I'll assuming that L is coprime to the characteristic. So the basic question is, so we're all familiar with the homology groups of this complex, which are particular which are finally generated ZL modules acted on by the Galois group. So they carry a lot of number theoretic information about X. For example, if K is finite field, then Weyl conjectures say that we can recover a number of points in K from the action of the Galois group on these objects. Actually, even when we replace ZL by QL, that's okay. But so the question is, so maybe the main slogan is that the total complex has more information, so contains more information, more arithmetic information than individual homology groups.
You write our gamma, you also mean phase change to KS, right? So our gamma of X, you do mean phase change to KS or not?
What do you mean continuous? Thank you. Yeah, gamma has to act continuously. That's right. So, so I assume that the actual gamma on ZL is continuous. Yeah. So we have this guy. And then if you do this with coefficients QL, then this is not so because by Deleuze's Hardy-Lefschetz theorem, with QL, this complex is quasi-isomorphic to the direct sum of its homology groups. So nothing of interest. By quasi-isomorphic to where appropriately shifted. And so the phenomenon is integral. So the interesting thing will disappear when you go from ZL to QL. However, here you may have something. So this question is very abstract, but in concrete calculations, this is equivalent to understanding the spectral sequence. I want to understand differentials in this spectral sequence. So we have the usual, so the geometric methodical homology groups, and they're acted on by the Galois group. And so we have, like, some people call this Leray or Hochschild-Serre spectral sequence, which converges. So this is E2 terms. Basically,
So you want continuous then on the side?
Huh?
You want continuous Hitachi homology,
yeah, absolutely. Yeah. Exactly.
I mean Janssen type, yeah.
I mean, they define it one way or another. Yeah, I mean, it's not so important. I mean, because okay, I mean, if you're confused with this, just replace that L by Z by finite coefficient Z modulo L to the N, and that then we can talk about these things. So one well-known phenomenon of this kind is that if there's a rational point, then we can split off in this complex. We can split off ZL. Then it's again quasi-isomorphic. And then I have to truncate it, starting with look I'm truncate. So this is the zero of cohomology group, and truncation is the rest. And this is simply because, so in the language of spectral sequences, this is simply saying that the natural map HI so that's okay, so for any I, we have this map which is just induced by the structure morphism X to spec K, and choosing a K point defines the splitting of this map. So it's just split off these guys. So in particular, all differentials that hit those groups must be zero. So if I can draw a picture of the spectral sequence, then I'm talking about differentials ending in these objects. So that's okay. So that's not very deep. But a question which is much more interesting is what happens to other differentials. So, for example, if you're interested in the Brau group, you need to know about differentials at the next layer, maybe that's are represented by maps going like this. So from and those are tricky to calculate. So okay, let me start with one case where we do have complete splitting of this complex. So, and that may be well known, but it's very hard to locate a reference. So, well, so theorem one says let C be a curve, okay, be a smooth, projective, geometrically reducible curve. And let's assume that it has a K rational divisor class of degree 1. So in other words, so equivalently, assume that this Albanese torser is trivial. And the Albanese torser is degree 1 component of the Picard scheme. So this has a K point. Okay, let J be the Jacobian. And then we have completed. So then
This is C, right? So your X is C.
no, it's J, sorry.
J.
Thank you. Okay. So in particular, the spectral sequence degenerates at the second page. So all these differentials will all be zero. And let me explain the idea of this. So it's, I mean, when I explain the idea, you all agree with me that it must be very well known. So suppose you have any principally polarized abelian variety. So so we are with some field which is separately closed. So and then it has a rational Kunert decomposition of the diagonal, but rational. I mean, that's very important. So we've okay, so there's a formula which I don't have time to write, which can be found in Tony Scholl's classical motifs paper. And basically it goes like this. You take lambda to be the principal polarization, and then I mean, you don't need many tools. You have projections and group structure. So this gives rise to morphisms from A cross A to A. So the projection to the first factor, projection to the second factor, and then addition. And then using lambda and those guys, you just create this sort of unit projectors, but they will have denominators. And they will have denominators which are, you know, some sort of factorials. And then, well, the remark, well, I've seen this in a paper by Junikins Su, that so I think this remark probably was made by other people as well, but that if we take A to be the Jacobian of a curve with a k-rational point, for example, but you don't need an actual point. It's enough to assume that you have a k point in the Albanese torser. Then you get the same thing integrally. So if A is J, as is defined here, defined as conditions, then magically the Kunert decomposition is integral, and that does the job. And the reason why it's integral is that because you have this super classical Poincaré formula. So now this is something which works for the Jacobians. So if if lambda is a canonical principal polarization of the Jacobian, so the theta divisor, then we have this. So, okay, I'm not saying what this equality means. I mean, like, maybe this is true in the Chow group or in cohomology, but let's not worry about this. And the point is that we can always canonically embed C into P1, into the Albanese torsor, whether or not C has a k-rational point. And if this torsor is trivial, if this torsor for the Jacobian of C contains a k point, then we can consider, so we can identify, it's isomorphic. I mean, it's choose an isomorphic of this guy with J, and then we can play the usual game. We can consider symmetric powers of C mapping to the Jacobian, and these cycles can be obtained by taking self-intersection of the canonical principal polarization of theta divisor, and then there is this factorial that appears, and factorials get cancels denominators. So denominators disappear because of this factorial. So that was the observation of well, I think many people, but at least this is in the paper by
You also decompose Chow mode.
yeah. Anyway, and then of course, if you have this formula, you just play with the same as derived category, and you get projectors in the derived category. I mean, there's little work involved, but that's the idea. Okay, so you don't need anything else. Okay, so, and as a corollary of this, we can extend this result to varieties, let's say to abelian varieties, which are direct summands of products of Jacobians of curves, each with a divisor class of degree 1, for example.
Where's the existence of a class of degree 1 used?
Oh, here, because I want to be able to identify this with J so that I have C embedded in its Jacobian. To give a map from C to Jacobian, you need to have a rational point usually, but you can make do with just take a rational divisor. Yes. Okay, and now in contrast with this theorem 1, I want to give an example where this is not the case, where we don't have this quasi-isomorphism. In other words, the spectral sequence does not degenerate. So that's going to be an example where we have a non-trivial differential, and this will also be a Jacobian of a curve of genus 2, but this condition will not hold anymore. So peak 1 is not going to be trivial. And actually, it's kind of amusing because you will see that ultimately the reason why differential is non-zero is due to some sort of Brown-Money abstraction. So I find this kind of fascinating. But maybe there's a different way of doing this, but I'm not sure. So theorem 2. Now let's see this particular curve of genus 2 of rational numbers. So this equation was taken from a paper by Brendan Kreutz, and I'll explain what Brendan Kreutz did. And so let's consider its Jacobian. So this is an abelian surface. And then the differential on the second page of the spectral sequence. So let me draw it. It's going like this from Okay, and the coefficients will be so I'm choosing L to be 2. Now, there is this very simple. If you take maybe I should have written this somewhere. Let me do it here. So if L is greater than I, then all differentials on the ith page of the spectral sequence. I think you remember which one. But let me just do it again. Well, let me write it down for any abelian variety. Just or it can also be semi-abelian variety, like in the title of the talk. R0. And this is a simple consequence of the fact that this spectral sequence is functorial with respect to endomorphisms of the abelian varieties. So we can choose multiplication. We can look at what happens if you consider multiplication by m, so the simplest possible endomorphism, whichever abelian variety has, and we exploit the fact that the multiplication by m acts on Hughes cohomology as m to the q. So you see there's this q here, and so if you look at the differential, for instance, it will be going from, okay, let's talk about this differential. It's going from 0,2 to h1k h2k h1. And so there's tension between these two degrees. Okay, there's 2 here and there's 1 here. So if you for instance take m to be -1, then it will act trivially on h2, it will act as -1 on h1, and so this map here must be 0 for any L other than 2. Okay, so I mean this is the same argument. Okay, so this is why I'm writing Z2. So that's the only case actually of any interest here. Okay, and the statement is that this differential is non-zero.
Are you not assuming characteristic is not 2? Or,
Say again?
sorry, are you assuming characteristic is not 2 or even characteristic over?
Absolutely, yes. I mean, but I'm going to be, it's going to be Q any, it's going to be Q anyway. But yeah, I mean, I'm always assuming that that L does not divide the characteristic. Yeah. There's no FPPF comp. I mean, maybe you could do these things with anyway. So FPPF cohomology is complicated. So let's not worry about this. Anyway, so what I'm saying is that this is non-zero. Well, let me again sketch the proof.
Is it the same statement with z modulo 2 to the power n?
Yeah. I mean, yeah, you can replace, for example, I mean, I will explain the proof with coefficient z mod 2. So I have to be quick because okay. Anyway, so the fact is that this differential. Okay, let me just assume from the start. I mean, there's the same statement with Z mod 2 here, and then now suppose to begin with I have any polarized abelian variety, not even principally polarized. So then the following is true. Here we have so lambda B polarization. And then its first term class mod 2 is an element here, and symbolization is defined of a k, so it's it belongs to this group, so it's Galois invariant. And then I know somehow the image of this class here. I know what this image is. So first of all, we observe that this H1 is something well known. Well, I mean, I'm writing dual. I know that J is self-dual, but this works more generally for any abelian variety. So using Kummer sequence, you get this well-known isomorphism. Okay. And this is the target of a map from H1 a J dual. So that's the obvious map, which you get the connecting map of the sequence where you just consider multiplication by 2. Okay, so use H1 goes to H2. And finally, this group receives a map from Neron-Severi the Gaussian invariant part of Neron-Severi. And let me explain this, where this map is coming from. This one is coming from the usual sequence. We have pick R, go into Neron-Severi, and we have pick 0 here, which I will identify with okay. So that's again a connecting map. So of course you guessed what I was going to say. So my polarization is a class in this Neron-Severi is Gaussian invariant, and I'm claiming that the image of lambda in this group is the image of Sverstern class in this group. So that's one thing. And now let's specifically assume that we're working with a Jacobian, so it has the canonical principal polarization. And then I can be more specific. So in this case, it's canonical principal polarization. I know the image of this class. This is pick G minus 1. So okay. And then yeah, that's big simplification. And okay, like 30 seconds. Let me kind of explain the fun part of this talk. So I mean, so why differential is non-zero? So we need to. So this is actually all due to Brandon Kreutz. I mean, this bit, but I think I must explain it. I really have to. Thank you. So, okay, so when G is 2, of course, this guy becomes peak 1. So that's just the Albanese torsor. So, and if you look at this, by what I just said about this situation, if you want to prove that the image of this one here is non-zero, we need to show that peak 1 is not divisible by 2. Okay. So that's exactly what we need to show. So okay, great. And now, so Kreutz had this idea, so that if K is Q, then we have, arithmetic geometry at our disposal. So far it was just pure geometry over any field. But now, if we ever, like as the previous speaker pointed out, there's number theory in this title. So this one, this Albanese torsor magically is I mean, there's a variety which is everywhere locally soluble, and so let's say, I guess, well known. So it defines an element of the Teicher for every group of J, and the Teicher group of J naturally pairs with the Teicher group of the dual abelian variety, isomorphic to J. So that's Castle state pairing. Okay, so that's a subgroup of H1 Kj. And so how do I check that this class is not, you see, my problem is that showing that this class is not, it's not the problem showing it's not 2 times something in SHA. It has to be different. It should not be divisible by 2 in this one. And so I you know, when you take the connecting map of the sequence given by multiplication by 2, you end up here. So we just look at the something called SHA1 K with finite coefficients, and that's much easier to understand because you know, don't need any assumptions that SHA is finite or anything. So we have the Poitou Tate pairing of SHA1 with sorry, it goes to SHA2, excuse me. So it's sitting here, and there's a SHA1 this like this. And these 2 pairing are compatible. So if I take my element sitting here, and I want to show that it's not divisible by 2 in this group, all I need to do is to find some element in this object. I mean, and this pairing is well, I mean, these objects are finite, and this pairing is not degenerate. So all I need to do is to find some element sitting here and to check that its image in this group pairs non-trivially with my class. And finally, using sort of Manin's observation that the Castle state pairing here can be restated in terms of Brown-Manin pairing, we just need to, I mean, that's something you can calculate concretely. And so, okay, so I have to finish very quickly. So just 2 sentences. So what Brendan does is he takes this curve. I mean, you notice that the right-hand side of this curve is already, not just the curve is everywhere locally soluble, but its right-hand side, which is a 0-dimensional scheme, is also everywhere locally soluble. So it's enough to work with this, I don't know, six points of a Q-bar, like, okay? And then you construct explicit, I mean, this can be made quite explicit, and you construct this Brauer class. There's something extremely well known. So C is a double cover of P1, and you have some basically quaternion algebra on P1, which you want to become unramified when you go to C. And that's very easy. All you need to do is to make sure that it has non-trivial residues just at the Weierstrass points. So that's the explicit construction of Brauer elements. And you know that these elements come from Brauer group of J. So kind of things really work very nicely. And the final calculation is just numerical calculation. That's why I didn't want these numbers. So this number 3 plays a role. And I mean, you end up just proving that this pairs non-trivially with something coming from here. So it's not twice another class. Okay, and maybe just in words. There was supposed to be like theorem 3 in this talk, but there's no time for it. And there's a general recipe for, so it's not just, I mean, like, this strange property actually comes from a general recipe for this differential, which is also quite beautiful, but I don't have time for this. And one last thing is that we also have an application to calculation of the Brauer group of tori. So I mentioned semiabelian varieties, which I said nothing about tori at all. So in the book with Jean-Louis, we had an open question about calculation of the Brauer group of torus, and using arguments like this one, you prove that some geometric Brauer group is killed by 2, or by a power of 2, and then there's a formula just like the one which I didn't show you, which works also in this case. And I have to stop. Thank you very much, and sorry for.